All right. So, yeah, it's me again presenting another slide deck of another PhD, this time not Maximilian, but Niels. And in this lecture, we're going to talk about large language models and maybe how to make them more explainable or more, let's say, trustworthy. So nowadays, LLMs are everywhere, right? In education, in security, digital systems, or healthcare. But there is a big question, can we actually trust LLM generation in critical applications, right? I don't want my LLM to do some crazy shit when my robot is doing some precise things in medicine or anything like the LLM. It should be trustworthy. So the main issues with LLMs are the hallucinations, right? Like outputting things which are just plainly wrong or which were not stated in any case or not grounded in actual information, where it just outputs more and more random tokens because it thinks that that's correct. So yes, so generated text is not factually correct and maybe also not faithful to the input context, right? Like if you input something in your model, then suddenly things, oh yeah, they're, I don't know, you tell it, okay, tell me what objects are on the table. And the VLM then says, oh yeah, there's, I don't know, some mark, but there is no mark, right? It just hallucinates things which are not there. So Niels did one prompting, what is the Informatikum in Karlsruhe? And yeah, well, maybe the Informatikum was too new, but the model had no idea what the fuck the Informatikum is. So it just outputs some random stuff that it's a key conference at KIT in Germany. Yeah, that's just, as we all know, false. So yes. Why does this happen? Well, as I said, LLMs are just a next token predictor, right? So if it thinks like the next token for after the Informatikum in Karlsruhe, which is actually correct, is a key conference, well, those four tokens had the highest probability to be chosen, right? So that's the main idea. And that's things which the LLM cannot verify, right? There is no internal logic for it to say, okay, maybe I do a Google search or whatever, which nowadays also is just LLMs or shit. But there is no way for it to actually verify the facts. And also the pre-training data, which currently is the whole of the internet, also has some contradicting information, right? So it's not always clear what information the LLM should output or what are correct and which are maybe old and outdated. But how bad is it? Because only looking at some qualitative examples is a little bit boring, right? Maybe there are also quantitative examples. And there is one, can barely read it, but I think it's about some legal mistakes in large language models, yeah, the law benchmark. And you can see that the mean hallucination rate, don't ask me what that means, how often it hallucinates, no idea, but you can see that the smaller models have a higher value compared to the bigger models. So maybe there's a trend to, okay, if I have a really, really large model, maybe then hallucination will stop. This is also supported by a technical report for GPT-4 of OpenAI, where you can also see that GPT-4 in general just has a higher accuracy in different in different fields, and accuracy meaning like when it was not correct, it probably hallucinated something. But the thing is, we should not necessarily trust better models because they only become better, but then we trust them even more, but they still will hallucinate. Like you will not get rid of hallucination only because you have more parameters, right? Just the network can still not verify if something was correct or if information is just outdated. So how can we mitigate this? Maybe you guys have an idea how to mitigate hallucinations. Yeah.
Throwing more information on it during the prompting.
So better prompting, sure. Yes.
Making the model explain itself.
Okay, how can you trust the explanation?
by having both sources and punishing all sources to train it.
All right, could work, but can still be hard. Like I remember, I don't know, a year ago or so, I prompted some LLM to give me some paper, and it gave me the link with the correct title, but the link always referred to some physics paper about black holes, and I was like, what the fuck? And I prompted it again, and it again gave me the same link. So could work, but it's always hard for an LLM then to explain its decision. If it already hallucinated, the explanation could also be hallucinated, right?
What if you would punish the model for giving an answer that isn't correct instead of just saying, I don't know?
Maybe. I don't know. The thing is also, do you mean with punish via prompting, or do you mean punishing during training?
During training.
Yeah, well, we can't try that, right? That's one big issue with those big LLMs. Like we can prompt them, we can maybe fine-tune smaller LLMs, but with the big ones, maybe it works. I don't know. Yes.
So I think maybe it's not that easy to verify what's correct and what's not, right? Because I think some people do like knowledge graph stuff with LLMs where they try to insert like some, to say like logical connections.
Mm-hmm. Yes.
I mean, it is more than possible to just prompt the LLM to say, I don't know, in the case it does not know. It just needs some techniques to let it do that, but to mitigate those hallucinations so that it does not output some vivid things.
Sure. Like there are different ways to mitigate hallucinations. The only problem is I think you will never get rid of them entirely. But yeah, one thing you said is prompting. There's also the model confidence, right? Like how confident are you with your next token prediction, which goes into direction of if you are not confident, tell me you don't know. And also consistency, like if I prompted multiple times, do I always get the same output? Of course, if I have a low temperature, so it's more deterministic, then of course, but if I want to have like good answers, then usually the temperature is not completely low, so I will have different answers, and sometimes they are correct, sometimes they're not. So we will now look at all three of them, and I think prompting is the biggest one with a lot of different methods. So already, as you said, good prompting can reduce hallucinations. As we have here, a prompt, what did the robot do in the following, or what task did it perform in the following observation? And the output is removing a pot lid from the stovetop, and I think there is no pot lid in the whole description, right? Like it just hallucinated this one because there is, let me read through it, because there's a stove, it just thought, okay, on the stovetop there was a pot lid. So what you can do, very simple, is just rely only on the given information, and then already the prompting or the result gets better. There is also the idea of prior knowledge. So we can do this by step, giving it more and more information about the task and how to solve it, and specify an output format. That's also very important. Like you can tell your LLM, hey, I need this in this and this output format. For example, something like a JSON file or a JSON structure and so on. And what Niels did here was he gave like very precise guidelines, so step-by-step guidelines, what should the LLM do? And then also told it, hey, I need this in this and that output format. And then, of course, if it still hallucinates and doesn't give you the correct output format, then you need to, again, prompt more, or maybe, in this case, give it maybe additional examples, right? You can give him one example how it should look like, and then it should output it. But if it still doesn't, then like give 1, 2, 3 examples. Yes, and then we actually get a very precise output referring to the different steps and the correct output. So there are best practices you can look at for good prompting, which already produce better results and increase interpretability, right? That's also an important thing. If my model actually outputs something in the format I wanted, it's much more interpretable for myself, and I can actually use it in a code, right? If I want in a code a specific output all the time, my LLM cannot just hallucinate and give me another output, otherwise my algorithm would just break. So the other idea is we can also use chain of thought. The idea here is that the model is not getting like a question and then directly outputs an answer, but it outputs the answer step by step. And I think almost all or a lot of the current LLMs for Gemini and so on, they also have inner reasoning, which is kind of like this step by step, right? The LLM first talks with itself, kind of has an inner monologue, which is also this chain of thought, like what should I do? Why should I put this out? Is this correct? Maybe I should think about it again, and so on. So give it a little bit of time, argue with itself instead of just outputting directly the answer. And this does work, these chain of thoughts things, but they only work on bigger models. So on smaller models, does not really matter if the small model is bad. It stays bad even if it outputs more in a chain of thought way. But for bigger models, it actually increases whatever the metric is, accuracy, I don't know, but it increases the score significantly, as you can see here on the red ones. Or maybe also the blue ones. But oh yeah, the blue one is only zero shot without chain of thought, but you can already see like it also gets better for bigger models, but not significantly compared to the chain of thought idea. All right. Then there are also some advanced applications. If we go back to robotics, we can use a VLA for action generation. And also here, the chain of thought reasoning can actually increase our performance. Like if we have a regular VLA policy and we say clean the sink, then it starts to output. It outputs some values for X and for the different angles of the robot, but it can't perform the task. But if we now say, hey, use some chain of thought or embody chain of thought, it first outputs like where's the gripper position, the different bounding boxes, then it has a plan, and it sees to it that it then executes the different tasks. All right. Yes. Questions until here? Or the prompting stuff? Yes.
Okay, like with the heat that couldn't the chain of thought also be used to fool the human and still get to the wrong answer despite hearing as though it would make sense?
Sure. Like there's no guarantee with those methods. They're just helping to get less hallucinations and to more trustworthy answers. But I would say all of the models are still, if they don't know and they're just not sure, they hallucinate whatever. Like, I think it's also very obvious in code generation or whatever. They just output stuff they think is correct, and then if you look at it closer, like almost every second line or whatever has some error in there because it just didn't know that the specific functions need other parameters and so on. But yeah, as I said, only methods for mitigating hallucinations. Until now, you don't get rid of them. Any other questions? All right. So the next thing we can look at is the model confidence. So as we all know, the LLMs are token predictors. So we have some token with a specific probability, and then the next token, and so on. And sometimes the confidence or the probability for this token is rather low. So maybe we can use this this probability or this log probability to say when the model is uncertain, and mostly this is in the cases of hallucinations, right? When it hallucinates it just does not know. It does not know what to predict next. So the token it predicts will have a low probability. And the thing is, we can't directly use this measurement to say if it's uncertain or not, because the scores need to be calibrated. And what that means is that each prediction probability P should actually reflect its ground truth likelihood. So, as an example, I give my model 100 my model makes 100 predictions with a confidence of 0.8. This means 80 of those predictions should be classified correctly. Otherwise, the confidence doesn't make sense, right? If it has a confidence of 0.8 and it suddenly only predicts correctly 70 of those classified things. All right. And here in the plot, you can see how this looks like for image-based networks. So on the left, we have the 5-layer LeNet, and on the right, the 110-layer ResNet. And you can see we want to have those bars, those blue bars, on the diagonal line. So if the model has a confidence of 0, then also 0 of the predictions should be correct. And if it has a confidence of 1, then also all of the predictions should be correct. And you can see for this small network, this actually works quite well. It may be even like there are some gaps that it sometimes is even better compared to what it thought it would be. And on the right for the ResNet, it's the other way around. It's overconfident. It's thinking it can predict it. It's much more confident in its predictions, but the actual accuracy is much, much lower, right? So it tells you, oh yeah, it has to be the cat class with 99%, but in the end it wasn't a cat, right? It was a dog. So it's much less, or it is not calibrated in this sense. The other network is actually calibrated. So this is the idea of calibration. Does my network, are the corrections correct in respect to the likelihood of them being predicted? Is this understandable? All right. So yeah, there's a measurement for that, which we call expected calibration error. And now the question is, does this work for LLMs? Because if an LLM is calibrated, then using this uncertainty can actually give us an idea when it hallucinates or when it doesn't hallucinate. So one idea from one paper was to measure the calibration based on multiple choice questions. So you say, hey, this is the question, those are multiple choice. What is your idea, which answer is correct? And then see what the probability for those specific tokens is. And yeah, I don't know what exactly to read from those plots, but you can read from it in the language models mostly know what they know paper. But more interesting is, what if we have open-ended sampling, right? Like this is for some multiple choice answers, but what if we actually have like a long text generation? Then we can actually just ask for the confidence score. Like we can tell the model, hey, verbalize even in, we can verbalize the confidence in token space or use numerical values, which we then tell the model, hey, tell me how certain are you with the things. And you can see here, it kind of works. Like, I don't know why they don't have other specific bins, but usually it looks like that if we have it verbalized with the probability of 4 guesses, that it usually has even is a little bit too overconfident. Yes?
I wanted to say that as well, that does not work too well for most models. For the newer models, this self-confidence evaluation works rather well. But for especially in the GPT world of things, mini and nano models are just correlating their answer with their confidence and has no value at all. While newer and bigger models kind of go into the correct direction. Otherwise,
Yeah.
it does not work.
That also confirms a little bit the chain of thought thing, right? Where also it only works if you have a big enough model. I guess that also goes in the direction that small models cannot generalize that well compared to bigger models, right? But yeah, model confidence could be or can be used in bigger models for this purpose. Then there's also the idea of model consistency. So we can leverage consistency as a measure of confidence, where the idea is that, for example, we can give the beginning of a Wikipedia entry, and then the model should complete the entry. And we draw n samples from the same model, and we measure the consistency with a different LLM. Could also do it with a human, right? I don't know how accurate then the consistency measuring with a different LLM is, but whatever. And then we can see like how many of those samples were actually correctly, or we then ask some specific questions and see how many of those samples actually have the correct information in them, right? And then we can see, okay, how consistent is the model? And if we, for the n samples, have like, I don't know, 90% consistency, then that tells us, okay, the model is rather confident, even when producing different outputs under different temperatures. All right. So that was it for model confidence and consistency. Do you have any questions about that? All right, perfect. So, and then we can also have hallucinations in VLMs. So if we provide an image, the LLM in our vision language model can also hallucinate things which are not even in the image. So this is also not good, right? If you have an unsupervised VLM where you input images and you expect that the description of the image is correct, well, it can happen that it says, oh, the faucet is turned on and water is running into the sink. There is a yellow sponge next to the sink, which all makes a lot of sense, but not in this context, because that's not happening in the image. In some other context, maybe, but not in this specific image. So what we can also do with the foundation models, which is now a little bit off topic of the of this whole reducing hallucinations, we can use them for goal-driven explainability. So the idea here is we have robot demonstration data, and as we heard earlier, like there is only 10% of actual labeled data, so there is a good reason to have an automated labeling process for robot data. And what we can do is we take the demonstration data, we feed it in some foundation models, and then we get language annotations of the data. For example, the robot is picking up the mug and putting it onto the right counter or whatever. And then we can use this labeling to actually train language conditioned policies. And this is what Niels did in a 3-stage process where he first retrieves objects. So we have this video sequence of different frames. He gives it to an VLM, and the VLM predicts what objects are in the image, right? Sometimes they are also unknown and so on, and they are also not consistent across frames. So what we then do is we do object detection, because we already know the objects. Now we can try to find them in the image with some object detector, and then get a scored co-occurrences where you can say, okay, in every image there was a cup, in every image there was, or in almost all image there was a blue cup, something like this, and then we get an idea of, okay, what objects are actually in those entire frames and what objects can just be thrown out because they are not consistent across all frames. And then we get a final object list. So this is the first stage. Now we have the objects in the image, which is important to label it, right? To have some language command. The next thing is we can now do an object-centric scene annotation. Because we still have inconsistent bounding boxes and segmentation masks, right? We can extract them from some off-the-shelf models like SAM2 or anything else. Or I think there's also a model called OWL to get bounding boxes. we can do mask propagation. So over the video, the masks should be always on the same object. So then we get consistent bounding boxes and consistent segmentation masks. And we can also predict the depth. I'm not sure if it should be predicted because it's from images. So there are models out there which can predict from an RGB image also the depth. Not perfectly, of course, but rather well. And then we can use this information to get the gripper positions, the object movements, the object relations, like which object relates to another one, and the object states. Object states could be, is the microwave open or not, or is the lid on the pot or not, and so on. So now we have a pretty good understanding of the scene and can use this understanding to then get a key state detection and label generation. Key state detection is important because if we execute a task in a video, at some point we will pick something up. At some point we will close something. So all those states are key states because then suddenly the relation between object changes, right? And then also the language command could change. Like if it's a long horizon task where we pick something up, we close a door and so on, then I don't want to have in the beginning directly the whole language conditioning with, well, the robot should pick up this, then close that, and then do this and that. But we want to have changing language conditions for the different frames. Therefore, we use the key states. And there are a lot of informations we can use, the gripper position, object movement on object relations. And the idea is now, if I think it were those 4 categories, if like at least 3 of those categories tell me something changed, like either the gripper position is somewhere entirely different, or the object moved, or the object relation changed, or the state changed of an object, then we can say, okay, this is definitely a key state. And then we can mark it down and say, okay, this one is important. And until here, we have a specific language command, and afterwards another one. And together with all those informations, we can actually have language commands for unlabeled robot demonstrations. And this then would look something like this. Any questions about the method? All right. So let's look a little bit of the results, key states, languages. So for like comparing with other methods, we can see here precision and recall, like the different epsilons here is, I think, for 2 different key state thresholds. And you can see that well, it's ours and ours gripper, that the method, which is actually called Niels, just so you know, that the precision and recall is much higher compared to the baseline methods we looked at, either for the kitchen play dataset or for the bridge V2. And the method labeled a lot of data, like I think 10,000 or whatever demonstrations, like a lot of data. And also an interesting thing is we then can use this data to train our robot policies, right? And if we take the labels or if we take the annotated data from the Niels method, we actually have not perfectly a success rate compared to human labeled data, but we definitely have exactly the same grounding as human labeled data. And I think the main thing there was that in cost ratios, I think if you have the human labeled data, it's something like $5,000 or whatever to label one of those data sets, or even more. And with the Niels method, it's $100, depending on how much you need for the energy of running the whole process. I think it takes like 2 or 3 days on some GPUs. And then you already have the labeled data with almost no significant success drop. And you can also like extend it to more and more and more and more data, right? Where with humans, you need more and more humans, and that's just like very costly. All right. Yeah. If you're interested in anything with foundation models, you can write to Niels Blank. He will be back in the 3rd of September, so until then you won't get an answer probably, but after that. All right. Do you have any questions before we go on 5 on 5? Yes?
What exactly was the grounding in the last slide?
Probably that the labeling of the robot demonstration makes sense in the scene you have there, because humans are lazy and they not always correctly label it. So there could be some YouTube link in the language guidance or whatever, and then it's not grounded, right? Because it's just random bullshit. And it could also be that the scene is just wrongly described or too short or whatever. Yes.
But why is that then so considered a success? Because there are differences in the difference between the success rates and the correct grounding rates from the Niels and the human. Right? So how do you explain this difference?
You mean the success rate?
Yes.
Well, probably because only because you're correctly grounded does not mean that your labeling is perfect, right? It could still be that that whatever you've written down, either as a human or in this case with the Niels method, that it's not super descriptive of the scene. It could be grounded, but there are missing details which humans can better describe. So that could be why the success rate here is lower compared to the human labels.
So there's also one more thing that or two things that I want to throw in there that I think should be clarified. So one thing is that at the very beginning when we started talking about Niels was like talking about like hallucination. How does this not address hallucination? It actually kind of does, because basically by introducing this manual chain of thought that we're doing, like basically this step-by-step like addressing, we have like less complex tasks at once that the VLM would have to solve. And in fact, you can actually see this, that like if we use Gemini or something like this as a like baseline for our models, right? There's significantly more hallucination and bad labeling happening than for ours, because we do basically this step-by-step approach, right? That's the one thing. And the second thing is that you still have to consider that here the evaluation is based on the policy, right? So the capability of the policy or the behavior model itself also plays into the success rate, right? And something significant that we figured out is that like at the end of the day, our like labels, so the ones that like Niels generated, right, are significantly more freeform and significantly more natural than labels that exist in current data sets. This is two reasons mostly, right? One is that how do you create language labels these days? Either you do crowdsourcing, and then what happens is that people become like lazy and just notice that like the interface tells like success or like successfully done this just by containing text. So a lot of the crowdsourced data sets contain YouTube links, contain like improper sentences, right? Like multilingual sentences and so on. So basically they quickly just throw something in so that they get the check mark and can move on, right? So lazy crowdsourced labeling is unreliable, right? So the alternative to this would be templated language. So you basically eliminate this unreliableness by saying like, okay, in the scene, X happens with Y, right? And then you basically have like drop down boxes which contain like different answers for X and different answers for Y, and the people just select those. So this is what we refer to as templated language. So in all of these data sets that models so far have been like trained on, right, have either been crap or templated, right? And that means that basically the performance also that it was always evaluated is like this. So when we actually first used Niels labels, right, we noticed that these models were actually horrible. They actually didn't perform well. Only when we dumped down the language generation and intentionally said like, okay, now you have to produce this templated style of language, right? Only then the policies actually learn something. What that tells us is that the current capability of these models, at least the ones that we use here for evaluation, like in particular, for instance, like Octo in this case, they're just not able to deal with free-form language, right? So success rate does not actually directly mean that the labels that you get are sensical, right? So basically, completely senseless labels would result in bad performance, but apparently also free-form correct language also results in bad performance. But that is due to the capability of the current model. Does this make sense?
Yes, but regarding the categorization, you
Yeah.
said there's crowdsourcing and there's this, categorical labeling
Template.
or template things. Labeling. What about Amazon Mechanical Turk?
Yeah, that's crowdsourcing.
That is part of it.
That is crowdsourcing, and that is in fact what most people use, right? I didn't want to mention it explicitly, but that is just normal crowdsourcing. You have things like in the Bridge V2 dataset, the one that we relabeled, there's like YouTube links to like Rick rolls or like to this doesn't matter by Acon, right? Like these things, like like there's mixed languages and there's like improper commands in there. Like so, yeah, AMT doesn't prevent like this kind of things. There's one way that prevents this. For instance, the Droid dataset has been labeled with a company, with an explicit company, but this is super expensive, right? Yeah.
Couldn't you have some people make labels and essentially pool the labels and have people decide which ones are good or bad? So
Well, what did you say? If you do this, what did you say? Like you have now double the effort in terms of like so the argument would be like you could generate labels and then you could have other people checking the labels. Checking the labels is almost as hard as generating the labels because you have to see the video and see if the language matches that. So you could just generate the label itself.
But you could, for example, throw out huge things. So you would have a higher quality data set, which would be twice the cost, but still.
I don't know if like having less duplicates necessarily makes it higher quality. Like duplicates in a certain way are actually can be beneficial, right? But again, this is alternatives, right? But again, Niels works actually really well. And there's follow-up work now that is not published yet, but it will be soon. Not from our lab, but another lab called Robo Annotator X, which basically does what we want to do afterwards to create a new VLM that is basically trained on the labels that Niels was generating, right? In order to create basically a VLM that directly produces this high quality labeling on robot video data. Yeah. But yeah, Robot Annotator X does a great job with respect to that. So they were just as fast as we were. But that's like I think that should address some of the issues. Yeah. Cool.
Right. Then let's do the 5 and 5. And then we should be almost on time for the.
Maybe one quick thing. Are we still recording?